Hi, welcome to the videos for week 2, in which we're talking about more of the specifics of motion like position, velocity, acceleration, and the whole idea of kinematics. So we're going to break this down a little bit and kind of go through each one of them. So we're going to start with position. So in order to determine a position, we have to say, okay, well, we'll have some coordinate system. We'll say maybe that's the spot that we're at. If we're going to do that, there's a position vector. It's usually given the term r vector because we often think about the distance from the origin is going to be some radius outwards. And so this r vector, if we assign some units here, so we could say this is in meters, so 1, 2, 3, and we'll go 1, 2, also meters, then I could say my r vector is equal to 3 meters x hat plus 2 meters y hat. So basically, for the position vector to make any sense, we have to have an origin, and then the position vector tells us our how far away we are from that origin. Now when we start talking about displacement, displacement is a change in position. So if I'm here, if I start here at point 1 and I decide I'm going to come up here to point 2, so going from there to there, that's going to be my displacement vector. So I had one position, so I could call that actually R1 would be equal to 3 meters x hat plus 2 meters y hat. And of course, because I'm going to draw over to there, then this could be R2, where R2 would be still 3 meters x hat, because I didn't move horizontally, plus 4 meters y hat. And my displacement is the change in position, which would be R2 minus R1, which when we go through it, the x hats all cancel out. Then we're going to have 4 meters minus 2 meters, so that would be equal to 2 meters y hat. So 2 meters up, as we have here on our picture. So position and displacement are both vectors, but when we end up talking about distance, distance is the scalar. So distance doesn't care about direction. It's just the total amount you've traveled. So a key difference between distance and displacement is if I start here and I move a certain distance to the right and then stop, and then move and go back to where I started, then in this case, my displacement vector is actually 0, because I started and stopped in the same spot. So that would be the total displacement. I would have one displacement and then another displacement, but the total displacement is 0. Whereas the distance would be, let's say, what's that? Let's just go 1 inch, because that looks like about an inch to me. So the distance traveled would be 2 inches, because I traveled 1 inch to the right and I traveled another inch to the left. And what often ends up happening is, I guess I should have done that in green, but that's fine. If you're talking about having some coordinate system and the path that you follow does all these weird things, and then it comes to here to that point, we say that's 10 meters, then delta r is actually really easy to calculate, because it doesn't care about your path, it just cares that you started here and ended there. So delta r would be 10 meters in the x hat direction, using the standard notations. So the distance, on the other hand, I would actually have to count up all of the different parts of that. So that's the little thing about position, distance, and displacement. So next we're going to talk about velocity. So average velocity, instantaneous velocity, and speed. So we'll start with average velocity. And in all cases, these have to do with the rate of change of position, well, rate of change of the things we just talked about with respect to time. So the average velocity, so the v, we do a little average there, is going to end up being the displacement over the change in time. So because it's talking about specifically the displacement, it doesn't care about the path. So for that sort of wiggly squiggly thing I drew earlier, it does all this path, comes to there, it's 10 meters, and the time it took for me to draw that, 2 seconds. So then V average is going to be that 10 meters x hat divided by 2 seconds, so 5 meters per second in the x hat direction. So while this whole path was being traveled, the direction of the velocity was changing at every point in time, but when we're talking about the average, that's where we just care what's the beginning, what's the end. So when we're talking about the instantaneous velocity, that's where we're saying that each point in time along this path, at this moment, it was going that direction. When it was at this point, so we could call this like V1, V2, up here, it's going to be V3. So in all of this graph, the instantaneous velocity is changing constantly. So it's always changing directions as it goes through the path. All right, so that's the sort of general idea behind that. If we actually want to get an idea of what the instantaneous velocity is, so that's where we don't need the subscript anymore, we would actually say the instantaneous velocity is the derivative of the position vector with respect to time. Now, this might start to seem to be a little bit complicated. We talked about derivatives in multiple dimensions, but if we're just thinking about one dimension, then that means the velocity is just going to be the derivative of our position with respect to time. And so in one dimension, this is an easy thing to talk about. If we're in higher dimensions, we'll have to talk about it a little bit more carefully, which we will do in the future. Now, when we're talking about speed, that's where speed, which I can never remember what variable I like to use it. We don't use v's because v is velocity, but the speed is the magnitude of the velocity vector. So it's just the way of sort of saying that during all this time, the speed might have been changing, the magnitude of it might have been changing, but the direction doesn't care. If we're trying to talk about the average speed, so this would be instantaneous. The average speed is actually the distance divided by the time. So speed more has to do with distance because speed is also a scalar, and so it deals more with distance divided by time, whereas velocity is a vector, so it has to deal with displacement and time. The last little bit, so acceleration, that's where we can again talk about the average acceleration, and that's where the average acceleration vector is delta v over delta t. And then similarly, as we were talking before, try to remember to keep going through my colors. So the instantaneous is going to be the acceleration vector is the derivative of the velocity vector with respect to time. And that's it. If we're talking about the one dimension, so if we go to one dimension, we basically are just going to end up removing all of the vector things. So the average acceleration is just delta v over delta t, and the instantaneous acceleration is just the derivative of the velocity with respect to time. So just kind of making sure that I'm talking about all the one-dimensional ones. That's where we're trying to talk about the average velocity. Well, that would be, that's supposed to be a delta 2. My apologies. That would be delta x over delta t. But then our instantaneous velocity would be dx dt. And then when we're talking about position, positions, x. And if you want to talk about, so this would be position, and again, displacement is delta x, which is often like x2 minus x1, or x final minus x initial. Could give it all sorts of different descriptors of that. So hope this helps give you an idea of where we're coming from when we're trying to go from position to velocity acceleration, or possibly the other way. If we have an acceleration, being able to integrate that to get velocity and integrating the velocity to get position. Thanks for watching my video.